Is titration. Titration is something you've done in both 65, 101. I don't know if you did an experiment in 102 yet, or if you did.
Yeah, we have.
All you're doing is you're taking something that's an acid or a base, you're putting an indicator in, and you're seeing where the equivalence point is. And we're going to discuss all of those things in the context of a curve, or different curves. And that's what this is, titration curve, the acid-base titration curves. Okay? So we're specifying acid and base things. However, towards the end, we're also going to try to figure out how to, do I have it on here? So this is just all kind of saying the same thing over and over. At the end, we're going to talk a little bit about how to determine what indicator to use to see that equivalence point. Okay? Same thing you guys have done. I mean, I think you looked at thionyl blue, and you looked at phenolphthalein up to this point in titrations, right?
Yeah.
So now you get a better sense of why or how those are chosen. Okay? And how to choose them yourself. Okay. You might have done a little bit of that in lab. Okay. No, this doesn't work that way. Okay. So there's nothing really new here. This is all stuff that you know. Once again, this is stuff you know. You have an acid in here, you have an indicator in here, you have a base coming through here. You control that as soon as you've neutralized all of the things here, the protons with hydroxides, you get the H2O, and then you see the color change when they're all neutralized. Nothing big there. So I don't think I need to walk you through that. That's a process you already know. Okay. This is what I want to talk about now. So this is the curve that you're going to look at. These are the titration curves. On the y-axis here you have the pH, and on the x-axis you have the volume of whatever you're titrating in. So if you have an acid and you're titrating in a base, this is a base. If you have a base and you're titrating in an acid, then this is an acid. And this is just simply the volume of that, in this case in terms of milliliters. Okay? Now I'm going to describe this curve as we go. That's going to be the majority of what we're going to talk about today in a couple different ways. I'm going to show you a curve for a strong acid with a strong base. Then I'm going to show you a curve with a weak acid and a strong base, and how this curve slightly changes and what the differences are related to that. Then lastly, we'll look at a weak base with a strong acid. The only thing we're not going to bother with is a weak acid and a weak base, because you can't get a curve that's going to make enough sense to use, so you would never use it. Okay, and I could discuss that or give you some insight to why, but you won't need to know it any more than that. Okay, so let's start here. We're looking, okay, when you think about a strong acid, strong base versus weak acid, weak base, for all the things that you know at this point, what are the differences? If I'm thinking strong, strong, or weak, strong, what comes up as different? Okay, actually, let me take a step back. When you think of just taking a strong acid and you put it in water, what happens? Dissociates. Right. When you take same thing with the base. Anything I say with the acid right now relates to the base as well, okay? Right. If I have a weak acid, what happens? Just a weak acid, I put it in water.
Dissociates partly.
Dissociates partly, right? You get an equilibrium.
Right.
Okay. Now I'm talking about, and remember, then we worked our way through making buffers where we had a weak acid and its conjugate base.
Right.
And sometimes we'd put things in to make that happen.
Right.
Okay. Now what I'm saying is, what if I have a strong acid and a strong base? Okay. And so what am I doing? I'm making sure you're aware of the different things, and I'm going to talk about this because you have to find the pH through different methods on each one of these kinds of things, right?
Okay.
When I find the pH for a strong acid, what do I do?
Take the Ka value.
H3O, the
Yeah, you can just
Are they
use
hydrogen?
just one.
I use what?
Stoichiometry.
Stoichiometry. Right? Which is what we just did in the buffer thing when we added the hydroxide and stuff like that, right?
Mhm.
Stoichiometry of the balanced chemical equation using the molar ratio, right? Okay. How did I find the pH for a buffer system?
After adding the strong base or strong acid?
Use the ice too.
Or before, even before?
I'm just
Either way.
making a buffer system, and I make the buffer system, it's complete.
Right.
How do I find the pH?
So I get my ice table or my chart.
Henderson-Hasselbalch
Then I go,
equation. But in order to get parts for the Henderson-Hasselbalch, you may have to
Do the chart then.
use an ice chart or an end, or ice with an equilibrium or an end, depending on what you're putting in, right?
Right.
Okay. So now I'm looking at a strong acid and a strong base. So this should be pretty straightforward. This is actually going back to Chem 101. But I want you to understand what you're looking at in each section that I'm talking about. So here, this in water on its own completely ionizes. This in water just on its own completely ionizes, forming this and this. So if I look at this salt here, the chloride, does it change the pH if I put that in H2O by itself?
No,
No. What about the sodium?
neither.
No. So if I completely titrate a strong acid with a strong base, what's my equivalence point in terms of the pH? 7.
7, right?
Absolutely. But if I'm dealing with a weak acid or a weak base, would it be 7?
No.
No. Because of the salt off of the weak acid or the weak base. So this first set is pretty easy. It's actually all based on stuff you already know, right? So you're calculating the volume of the base for the equivalence point just based on putting in a certain amount here versus here. So in other words, I have 25 mils of 0.1 molar HCl. I can figure out the moles of HCl. It's a 1-to-1 ratio. So then I need to figure out how many moles of 0.1 molar sodium hydroxide I need to do to neutralize it. All I'm doing literally is neutralizing it there. It's no big deal. That's all stuff you know. So the next part of this is just that. I have this here, 0.1 molar, and I have 0.1 molar. I'm using 25 mils. I don't know how many mils I'm gonna use here, but I could figure out my moles here, or my millimole, and that should equal itself.
It will react.
And then I could figure out my mils here. And then I know how to neutralize it. No big deal, right? That's all stuff that you guys are familiar with off basic titrations. So that's the number I'm looking for right there, the 25 here. Because I didn't have the amount I'm using of the sodium hydroxide. Okay. And this is this is all saying the same thing we just did there. This is just laying it out in one long chart unnecessarily. Right? Okay. Now, I want to point out, does that automatically come up like that? I'm having all kinds of problems with this. I don't want this. This is what I want. So here is a titration curve for that process we just talked about, a strong acid and a strong base. Now, if you notice in that, I started with a strong acid, and I titrated the base in, which is exactly what you did with the phenolphthalein, okay? And then if I start with a strong acid, remember, this is the pH here. Am I starting higher on the pH or lower on the pH if I'm starting with a strong acid?
Oh, low, right.
Okay, so this spot here is before I put in any hydroxide. This here is just the strong acid.
pH, right?
The pH of the strong acid, that's it. Then as I put in some, in terms of mils, sodium hydroxide, here, you could see that this slightly moves up through here.
Start making water.
And then all of a sudden, I get this steep jump to the equivalence point, which strong acid, strong base should be at 7. And then if I continue to add, then it eventually comes over here, and now it's just all base because that's all I'm adding. There's no more acid.
You used stuff to that.
That's what the chart looks like for a strong acid, strong base. So, the pH changes rapidly near the equivalence point, which is also why I can use the indicator, right? So I couldn't do that if I had a weak acid and a weak base because it would be very flat. It would be hard to find a spot where I get that quick change. Okay, so that's why we'll talk about it. This is really frustrating here. Equivalence point is at pH 7, only for the strong acid, strong base. I want to make that a point. Okay. Now, the other thing is, I've mixed, and we won't be talking so much strong acid, strong base, this is pretty straightforward, but I've now mixed, like I mentioned phenolphthalein, I put phenolphthalein in here. So what do you think's happening with the indicator in this?
It's reacting to the pH, like it.
It's reacting, so I'm gonna have some form of the indicator that shows clear or doesn't show anything in this range. And then once I hit this point and it starts to become basic, it's gonna look a different way. So the molecule itself has changed. Okay, so I wanna kind of introduce that now. All right, and I think that's all I really care about here. Okay, I think I'm gonna stick with that for the strong acid, strong base. That's all you really need to know for this chart. And this is just saying the same thing there. Okay, here's a basic problem. This is exactly like what we just looked at on the, prior to the chart. You simply have 50 mils of this molarity sodium hydroxide is titrated with 0.2 molar nitric acid. Calculate the pH after adding 30 mils of the nitric acid. This is pretty straightforward. You're just finding the moles of each one and then subtracting out the number. Whichever one has more moles, that's what you're going to have left, right? And then you put that in terms of concentration. So I have 50 mils plus 30 mils, total of 80 mils. So I take whatever is left, I divide it by that. If I have more acid, then I simply put it in the negative log and I find the pH, right? No Henderson-Hasselbalchs needed here, right? Because it's strong acid, strong base. Maybe I want to do one more thing here now that I think about it. What would this curve look like if I was, in this case, I'm titrating the hydroxide or the base into the acid. What would this look like if I reversed that? If I started with the base and I titrated the acid?
Just the same, flip it.
Thank you. Okay. So this would start here and it would just reverse. Okay, I just want to make that clear for those of you that might not have seen that. So, because what's happening here, the sodium hydroxide is titrated with the acid, so that's the reverse chart. Okay, I want to make that clear. Now, 50 mils times 0.2 gives me some mole.
10?
0.2, what do I have?
10 millimoles?
Is that what it is, 10 millimole?
Right.
Okay, and then 0.2 times 30 gives me something, so let's see what we get here.
You get 6 millimoles?
Okay, so I get, as you said, 10 millimole from this, 6 millimole from that. All of this is gonna go, right? And that's gonna leave me with what? This is a 1-to-1 ratio. That's gonna leave me with?
4 millimoles of NaOH.
4 millimoles of NaOH. So is this gonna be acidic or basic?
Basic. Right.
Where am I at relative to the equivalence point on a chart?
You're
I'm still way up above.
Right.
I haven't even gotten near the equivalence point here yet, right?
Okay.
This graph starts here and comes down like this. All I've done is I've slightly moved it over here
It's the only reactant.
by putting in the
Acid.
acid. In this case, what is it? Nitric acid. Does that make sense, what I'm doing here? What if this question changed and I just said, how much do I need in order to get to the equivalence point? Then what am I doing?
You'd have to add 10 millimoles of it.
I'd have to add a certain volume in order to get 10 millimole
Right.
here.
Oh, okay.
So you
And
had-
then I'm at the equivalence point. Okay, everybody see that? Just putting this in a couple different ways on a more simple system before we get into a little more challenging system. Again, I saw a hand.
Oh, I think I got it. Yeah, I understand.
Okay. So then from that, then I have my endpoint here is 4 and 0. And now, what I'm doing, there's my hydroxide. Don't forget, that's just the amount. I have to put it over the volume to get the concentration.
And you know it's hydroxide because it's 1-to-1.
Because NaOH is only what's left.
Left over, yeah.
That's the only thing that's left.
Okay.
Once again, this is a strong base.
Right.
I don't need to have that sodium there, right? What is the sodium there? What do we call that?
Like
Spectator.
spectator,
It's
right?
not doing it. But you see how why I say it like that. It literally, if I got rid of the sodium there and the sodium there and the nitrate there and the nitrate there, what am I looking at?
Just
I'm
based
looking
on
at the net
acid,
ionic
yeah,
equation,
yeah.
the only things that are happening. So this is basically
So-
hydroxide, and I don't have any acid left or any proton left.
So if you switched it around, you had 30 mLs of the NaOH, and like you switched it around, then you could use.
You'll
the
be
negative
past your-
44/80, would then be the acid if you switched it around. If
Yeah.
you switched
Well,
the-
there's no negative, there's just before,
Okay.
right? This, because it's a strong acid, strong base,
Oh, because it's a,
it's,
okay.
yeah, you're not, it's not minus x plus x in this case. It's just whatever balance, I have 6 here, I have 10 there. 6 is gonna bind to 6 of those in the 1-to-1, and I'm gonna have 4 left and 0 left, that's it.
Okay,
So if I could flip, if I flip the volumes, that would flip, but that's assuming I have the same molarity, it's also assuming what? My balanced chemical equation is a 1-to-1
1-to-1,
ratio.
right. Mhm.
What if it's not a 1-to-1 ratio?
You gotta multiply it.
I gotta use that 2, if it's a 2 or 3 or whatever it is, in here, because that's how many I'm getting,
Right.
right?
yeah.
For example, and this will come up later, but if I have calcium hydroxide, I break that up, what do I get? Calcium 2 plus 2 hydroxide. So for every hydroxide that I get, in this, if I only had HCl, I'm only getting 1 H plus. So I need 2 of these to match that.
Right.
Okay, that's why the balancing is so important. We haven't really dealt with that in the ice charts yet, if I recall. And we'll start dealing with that coming up.
Really?
And that will play a bigger role, so that's,
And the 2x?
I think we did 1 or
Yeah.
2 examples, but not as many. We're gonna do a lot more of those probably coming up. Okay, so are we okay with this? This is just all stuff you know pretty much.
Right.
Okay, so then I get the hydroxide concentration, 4 millimolar divided by 80 mils, gives me 0.05 molar. I put that into the log, and I get some number. I take 14 minus that number, I get my pH. Okay, so there's the POH 1.3, 14 minus that is 12.7. Does that make sense? Yes, because it's basic.
Basic, yeah.
It's and it should be strongly
Pretty basic, yeah.
absolutely. So that should make a lot of sense.
Mhm.
Once again, this is not that challenging. There's nothing new here, basically. It's just being presented a little bit differently. Okay, so here's an example of what I mentioned before. So now I say I have 50 mils of this, and is titrated with this here. Calculate the pH at the equivalence point. Well, the first thing you would say is, if this is a question, you would just say pH is 7, right? Because it's a strong
An equivalence,
acid
yeah.
and a strong base.
Right, equivalence.
It's the equivalence point,
Mhm.
right? But if I wanted to figure it out, I would just have to make sure that my moles or my millimoles cancel each other out.
Mhm.
That's it, right? Okay. So once again, this is not that challenging. So here I just make sure that I have 10 and 10, gives me 0 and 0, and that gives me a pH of 7, neutral. But you could have figured, you didn't need to do all this to figure that out if I had a strong acid and a strong base. And that's because the conjugate acid and the conjugate base are pH neutral. So therefore, they're not going to move it up or down. Go ahead.
No, man. Actually, I was trying to find out the other 50, but it's actually from at equivalence, from the,
Oh, so if you
Sample.
weren't sure how to do this, so for example, if this was a strong acid and a weak base, or a weak base and a strong acid, and that's what I'm trying to get through a little faster to get to that, where it's a little more challenging, then the key here would be to make sure that these are the same. So if I have this, I'm
Right.
given this, right?
uh-huh,
Then, and I'm given this,
uh-huh,
then I figure out this from this data.
okay.
Now I can figure out this, because I know this has to be equal at the equivalence point, then I can take this and this to figure this out,
So even if you get a different molarity for that one, okay.
right?
See, yeah, yeah.
And that, yeah, absolutely, it doesn't have to be 0.2, this could be 0.3, this could be 1.5, this could be
You find your,
0.202, whatever.
right, okay.
Once I found the millimole here,
Mhm.
I just have to match the millimole here,
Right.
or inversely. And then based on the molarity in the millimole, I can now figure out how many mils of that I need,
Perfect.
right? That's everything you guys have done many times. But just maybe a little bit. Once again, here it's easy. This won't matter because it's automatically pH 7, strong acid, strong base. But when I get into a weak acid with a strong base or a weak base with a strong acid, that's going to change, right? And so that's what I'm leading you into now. So this one should be automatic. So on an exam, I ask a question like this, you shouldn't need to do all this. You should identify it quickly, pH 7. That's the equivalence point. Okay, this is another one, so I'll just skip through this. So make sure this is nothing different. 30 ml sample, titrated with 0.12. Okay, the pH after addition once again. So the only thing I'll point out here, I'll let you do this at home, it's not asking for the equivalence point here. It's just asking for the pH based on these amounts. So that means I'm given a volume with a concentration, and then I'm given another volume with a concentration. I figure this out, I see what I have left, and then I just solve for the pH that way. That's it, right? So I have 30 mils of this gives me 3 millimolar. I have 20 mils of this gives me 2.4. So 2.4 minus 2.4 is 0, 3.0 minus 2.4 is 0.6, etc. Then I have 0.6 of the H plus. I take that 0.6 in terms of millimole, and I divide it by 50 mils, the whole thing. That's my concentration. I put that into the negative log. I get the pH. I should end up with something that's a low pH because I have all H plus left, or 0.6 of it left. Okay. So these should be pretty straightforward. 1.92, that should make sense. Okay. Now let's get into something new. So we've now spent plenty of time on what we already know. Now we're going to look at a weak acid and a strong base. Okay? So here, let's look at the curve. I have the same thing here, pH, and the volume of the sodium hydroxide I'm adding in. The very first thing I want you to notice is where should this piece here start relative to the strong acid? Should it be higher on the pH or lower? Just the start part.
Should be less acidic, so higher.
Exactly, less acidic. This should be higher. So the strong acid should be the lowest starting point here, and as the acid becomes weaker and weaker, it should move up higher and higher at its start, before I've added any base to it. I've added no base. That's this part here. Now, you do see now, as I add the base, it moves up to here, and then look where the equivalence point is. Is it at 7? No, it's above 7. Why?
Because when you add a strong base to a weak acid, you create conjugate base?
Yes. The conjugate base of the weak acid, what does that do on its own in water?
It creates basic.
Creates-
Basic solution.
And this is important because I'm separating this out into what's happening. The very first thing that's happening here, I have a weak acid, so let's say C2H3O2. I don't know if that's what it is, but it could be. Okay. I'm now adding NaOH, and after I add the molar ratio that's equal,
Right.
this should all cancel out this, and I get H2O plus sodium C2H3O2. Everybody's good with that, right? This is at my equivalence point, but in there, I have this and here. If I take this on its own, C2H3O2, and I add that to water, what happens?
Creates hydroxide
I
and
get
makes
the
more acid.
C2H I get this,
Back
right?
to the acid. Oh, okay.
And I also get OH minus. That means that I have OH minus in there, which means that my pH should be above or below 7.
Above.
Above. So my equivalence point by a weak acid titration with a strong base is above 7. At the equivalence point. Does that make sense? Everybody see that?
Yeah.
That's why we went through that whole solubility salt thing. Okay. Now, the second thing I want to point out right now is if I had a weaker acid than this Should it start above here or below here before I start adding the base?
Above.
Above. If it starts above, where do you think the equivalence point is? Is it above here or below here, or the same?
Above.
It would be even higher. I'm pointing this out because it's important, okay? The weaker the acid, the higher it starts, also the higher its equivalence point is
Right.
when I titrate the strong base to it. Does that make sense?
Mm-hmm.
Okay. Good. Now, the next thing I want to point out here is there's a little bit more of a slope, right? So if I take this 2 across and take the angle there, this is going to be a little higher angle than it would have been with the strong acid, strong base. Okay? And this region here is what? What can that, what do you, when you look at this part of the curve before the equivalence point here, what would you think of that as? Remember, I have a weak acid here.
That's where it's
I've
creating.
titrated some sodium hydroxide in there.
Oh, so it's like a buffer.
It's like a
Yeah.
buffer,
It's
yes.
creating that
Like a
conjugate.
buffer.
Yeah.
This is the buffer region. Buffer ring before the equivalence point. Because after here, is there any buffer there?
No.
No, all you have there is a whole bunch of
Use
strong
that.
base, right? You
Yeah.
have a bunch of OHs in there.
Mm-hmm.
So are you getting a feeling for where these curves are, what's happening on these curves? Okay, good. So here's my equivalence point, the weak conjugate base. And of course, as I keep putting in OH, this is just simply a whole lot of
Whole lot of-
base. Nothing's happening there. There's nothing else there. There's no more acid. Okay?
Could you then use that as a buffer? It has so much base in it.
In here,
Yeah.
you only have base.
It doesn't have any.
There's no, there's no acid, right? The buffer needs the acid-base combo.
I mean, it will be a buffer if you add in the acid now. If you add in
then
a
you
strong
start
acid, you're
going
going the
back.
other way.
It's going the other way. It's not buffer.
Right. No, but it will be the buffer part, no?
No, buffer is able to handle
Uh-huh.
either the addition of an acid or a base.
Right.
That can't, if I put in more base, that there's nothing.
No, I
happening.
mean, if you add acid now,
I think what Orly's saying is just instead of going
Going the
this
other way.
you go down this way. If, no
But
matter
this
which
is a
direction-
strong, but this is a
But
strong
no
base.
Yeah, you have strong.
This
base,
is a
but-
weak acid.
oh, yes. It would have been a weak base, that would
If
actually
this was
make
a
the
weak
buffer,
base,
yeah.
but then this chart wouldn't make any sense. You wouldn't be effective because then you wouldn't have any sharp jump here, it would just be more flat.
Right. It would
You wouldn't even be able to figure
7.
that out because you wouldn't be able, you couldn't use an indicator there. There's not a
Yes.
sharp jump,
We go back to the other graph.
Yeah.
Yeah,
right?
right.
Is that okay? And do you see what the issue was there?
Yeah, I thought he was
Yeah.
asking
Okay.
something else.
Okay. Okay, so initial pH is higher, pH slowly changes in the buffer region, and the equivalence point is greater than 7. Oh, one other thing I should point out.
Hydrolysis of water.
Half the equivalence point, this is half of this, the pH equals the pKa.
Half neutralization.
Hmm?
I think it was called half neutralization.
Half the equivalence point. This is kind of a tricky thing of what I'm actually saying here. So how do you guys interpret that?
But it's halfway to the equivalence point.
What is halfway?
The pH.
So when you're.
That's
in-
exactly why I'm saying this.
But the
That's
difference
what
in
it looks
pH
like.
Is halfway.
This is, so what's the pH here? About 2 point something?
Yeah,
What's the pH here?
8.1.
Is that half?
No.
No. Which is exactly why I'm bringing it. It comes across strange. So what half am I talking about here?
Half of how much it takes to titrate.
Half of the volume of the titrant.
Yeah.
So here is about 25, so about 12.5, let's say this is 5, 10, 15, 20, 25, 5, 10, 15, somewhere here. That's half. Half of the titrant put in. What am I referencing there?
Moles?
Moles, absolutely. I've neutralized half of the acid at that point. That's what that's saying. And when I neutralize half of the acid, I now can say half the equivalence point, this is the equivalence point, half of it is where the pH equals the pK. Okay? pH of what? Let's make sure we're comfortable here.
Yes.
Of the acid,
Yeah.
absolutely. I want to make sure that those points are very, very clear,
Oh, that's when you have that ratio 1-to-1,
Right, so that's why when you have a buffer, you want.
that region.
that 1-to-1 ratio. Nice,
pH equals the pK, right?
perfect, yeah.
Closer to that?
Which
That's
is
a
at
buffer,
LN1.
remember?
Mm-hmm.
Okay.
The Hasselbalch.
And then if I go 10 points off, 10 points on, you go to either side, somewhere around, okay, good. Okay, so those are subtle things that are very confusing most of the time when you've heard it. And if you look at it your own, you heard exactly what you guys thought. Well, that, it applies, it's like half the pH, it's not half the pH, which is really, really important. So keep that in mind. And once again, if you're on a test or something and you're trying to figure something like that out, and you do get confused like that, you should just simply, and just like anything else, just like I did here. If I took this here, and I say this is under 4, this is above 8, that can't be half. Right? So you can kind of figure, but if I did this and I said, well, this is 25, this is 12.5, that is half, so it must be referencing that just to keep things like, and then in place. Just plug them in and see what happens, and then you'll reorientate yourself. Okay. Now, this is a chart I mentioned before. This is something I mentioned before. Here's my start point here. Here's my titration point here. So this line here indicates my equivalence point, and this here is my starting point of my acid. The stronger the acid, the lower I start. The weaker the acid, as I go up the Ka's here, the higher the starting point on the pH, and therefore the higher the equivalence point relative. Okay, and we'll revisit this, especially when we get into indicators. So I want to make that, I think I already mentioned this, but here's the illustration for this,
I like this chart.
right? That means that the equivalence point of this is somewhere, if I follow this line, is somewhere maybe around here. Oh, for this, the strong, it should be 7. This one, it should be a little higher. For this one, it should be a little higher, et cetera, et cetera, et cetera. Okay? And that matters a lot when I'm determining indicators, because I want to get it right at that spot.
Right.
Okay. Okay. So now we're going to look at, what is this? We're still titrating a weak acid by a strong base, I guess? Or did I go back? Oh, summary. Okay. So the pH is calculated as ionization of the weak acid. Oh, I see what they're doing. Okay. So, God, I'm kind of stuck here.
Starch acts as an indicator because it's also changing its properties, its molecule.
What's that?
Starch.
Starch.
Uh-huh. We used starch for last experiment where we were titrating with the.
Let me go through this and we can, I'll look at that later.
Mm.
If it still works, does this work now? No. So this way? No.
Batteries.
Okay, so the first part here, right here, you just simply figure out the pH by the ionization of the weak acid, right? How do you do that?
So,
Ice chart.
Uh-huh.
Just an ice chart, right? No big deal? Okay. If I'm over in this range here, how do I figure out the pH?
Hasselbalch?
This is the buffer region.
Right.
Yeah.
Hasselbalch equation.
First I do the ice chart,
Yeah.
or whatever I need, right? Ice charts, and then I go ahead and use Henderson-Hasselbalch. Okay? So we call that stoichiometry, which is basically the ice chart, with the endpoint. And then if I want this here, pH is calculated through hydrolysis of the salt, the conjugate acid or base. In this case, it'd be the conjugate base, right, from the weak acid. But if it was inverted, it would be the conjugate acid of the weak base.
That's
Right.
what we're about to talk about next.
Yes.
Yeah.
Right? So that makes sense there. Go
I
ahead.
have one more question,
Sure.
Specifically about that. So when you start with an acid and you titrate it with a base, it would still look like that when you have when you have both strong. But then when you start with a strong base with a strong acid, it would go the other way too.
Absolutely. Yeah. In fact, that's what I mentioned. Remember I went back and said what would happen? That's why I did that, just to
Okay,
give
I
you
just
that
wanna make
feeling.
sure.
Yeah.
Oh, no, it's
Yep.
just-
Okay. Okay. So you figure out the pH through very similar techniques, but of course, you're not using Henderson-Hasselbalch over here, and you're not using it over here. You're using it in the buffer range. Okay. Now we're going to do some problems. These are the same kind of problems. I don't see the need necessarily to do too much here. Let's just, you have 40 mils of this here, So you have this, and this is at this concentration, so you can figure out the millimole, same kind of thing. It's titrated with 2 molar of this, and then you're using 5 mils of that, so that gives you this, right? So then as a result of this, I end up with 3 moles, 3 millimolar of this, 0 of this, and 1 of this, right?
Yeah.
Just get rid of the K's, and you can see this would be a minus and a minus.
Mhm.
This is a weak acid, strong base. Different than a strong base and a strong acid. I'm starting with a weak acid, not a strong acid. Right, so this is a weak acid, so now the same titration kind of thing. But now I end up with, oh, it worked well.
Just needed a break.
So now I get the 301, what do I have now? I have a buffer.
Mhm.
I have the weak acid and
And the
its
Oh.
conjugate
Conjugate.
base.
Right.
Yeah,
So where is this on that curve? Somewhere over here, right?
yeah.
Okay, good. So now I can figure out, the concentration of that thing there, and then I can go ahead and figure out the concentration of this thing. Go ahead.
I just wanna make sure that I'm thinking about this right. Where did you get the, amount from the,
5 mils.
no, for the KNO8 too? For the-
This, 40 mils.
No, the conjugate base, right there, yeah, that one, how did you get the?
This,
Yeah,
What is the base?
if I use if I start with 4 of this,
Mhm.
and remember this is strong, so this is gonna neutralize 1 of those. That leaves me with 3.
With the 1 pool.
What's left? Remember, this is just neutralizing the H, what's left?
The NO.
Produces that.
But there's only so many Ks where potassium can transfer over.
Maybe I should do this.
The ice chart will block the C.
Do this.
It's just the-
I have HNO2, right?
Mhm.
Plus OH minus.
Or is that
Literally,
in
that's what
between?
that's what it is, right?
Yeah.
And that's gonna form NO2 minus plus H2O. Does that look better?
yeah.
Okay. If I start with 4 millimole of this and 1 millimole of that,
You can only get 1.
this is a 1-to-1, so I could say minus 1, minus 1,
And then, and then,
plus 1. If I do it that way, that helps, that's the change.
yeah.
That leaves me with the ending of 3, 0, 1.
Okay,
Is that okay?
yeah, so it was, you're using the,
Well, this, but if I had 2, 3, if I had 5 of this, then I'd use all this up and I'd be left with something basic. This is just neutralizing in the stoichiometric ratio the proton. That's all I'm doing. Okay. Okay. So now moving forward, I now have this is, that's my acid, here's my base. Now, once again, remember, I have to put those together, the total volume.
Total volume, yeah.
Just like we did last lecture, I think, or
Yeah,
maybe
last
2
lecture.
lectures ago. Okay, and now if I do the Henderson-Hasselbalch, since I'm in the buffer region, so I could use that. And here's did I have the peak, I must have had the Ka earlier. There it is, so I can turn that into the pK, right?
Mhm.
And
Negative log of that.
this gives me 2.86. So now this is just a problem that we've done with buffers,
Mhm.
right? So what's the next kind of question I'd ask here?
What's the difference,
what's the
maybe?
equivalent?
Change?
Thank you. What's the equivalence point? What would I do? What would I change here for the equivalence point?
I will make them equal to each other.
Make what equal?
The
Oh, so you
concentration, the molarities.
have to make the millimoles
Yeah.
equal to each other, so, yeah.
I make the millimole equal to each other,
Mhm.
and now I'm at my equivalence point.
Right.
And then you find out how much conjugate base you have.
But now I don't use Henderson-Hasselbalch, right?
Yeah.
So what would I do? I would simply take the base, the conjugate base,
Mhm.
put it in water. I could figure out how much conjugate base I have through this, right?
Right.
That's what I start with. I put that in water, and I form the other, and from the ice chart, I could now figure out the pH of it. The same thing we did 2 chapters ago, or 1 chapter ago, or whatever we did.
One chapter, yeah.
Right.
One chapter.
But do you guys see what's going on? This is, So where I have a lot of people get lost is that this is the equation that you start with. Now, I'm simply saying I need to map for the equivalence point. Before I just gave you a couple numbers, you put them in, that's what you get. I asked for the equivalence point, I know I have 4 millimole, I now need 4 millimole here.
Mhm.
They cancel out. Okay, 4 minus 4, leaving me with 4 over here, right?
Yeah, -4 minus
So now I'm looking at this thing, and I put this now
into water.
into, thank you, into water. That's exactly what I'm saying.
Again,
And then what
OH.
happens, I get this, and I get
OH.
this thing now is now reversed here a little bit, right?
And OH.
Plus the OH minus. So this is how I know it's gonna be basic,
Mhm.
okay? And I know what I'm starting with here,
4.
whatever this was, divided by the total volume. Okay, and then from that, this is, subtract x, add x. I find the OH concentration through the same techniques we learned originally when we learned the ice,
Right.
right?
1 to 1
Okay, so this is gonna be plus x, this minus x.
minus x. Yeah.
Sound familiar?
Yeah.
Maybe you forgot about it already?
Yeah.
Right? And then we assume that the x over here is so small, it's negligible.
Uh-huh.
So, and I know I gotta find the KB of this. Do I know the KB on this one, since I'm looking for this?
Yeah.
Find the K.
I have the Ka, right?
Yeah.
So it's KW divided by Ka gives me the KB,
Right.
okay? And then I can figure out what the POH is, and then I can convert that to the pH.
-14. Yeah.
Okay, good. This is just.
14 minus that.
Yes,
Mhm.
yes. Okay, so that's good. That is the next question, pH at the equivalence point. So now, what am I trying to do? I'm matching those, so I know how much of this to now add. Okay, 004. I now reverse, I put that into the different equation, just as I did here, and you gotta be able to follow each equation. That's exactly where the problem is, right? If you're not following where you're at, remember I told you a long time ago, make sure you know the equation you're working off of, right? That means that in this class, it's more than just following the numbers. You gotta intellectually understand what's happening so that you can then put in the proper equation and then you solve according to the techniques you know on how to solve, right? These things build on each other, and a lot in this class, as you see. So I needed to know this, then I needed to know this. Right, so I can't just bypass a topic and then think I'll just be okay later on. No. You gotta understand it. If you're not sure, you can come talk to me. So I figure out my concentration here for this. There's my KB, right? This is the KW. That must have been the Ka given. And then I get this thing, and here's I'm bypassing it, but this is x squared over this, right? This minus the x, but the x is irrelevant. So then if I look at, I put this in there, here's my KB, I move the 0.0667 up here, this is squared, I square root, which is what I'm at here. I get this, I put that into the log, I get the POH, I take 14 minus that, I get this, and that's my pH. Obviously, I'm moving through a little faster because the expectation is you already know those things.
Mhm.
I'm just kind of guiding you through the process. Is that okay? A little trickier. That question's a little harder, and so therefore that's a great test question, right? It kind of puts in perspective all these kinds of things and what's happening. You can see that as being one of the problem solving within the exam, right? So is this okay? Everybody see what happened there? Once again, as I go through it and I'm walking you through it, it's much easier. Make sure you could do a problem or two like this on your own. Okay. Okay, so now we're gonna do the exact opposite here in terms of the chart. And now, because we're looking at a weak base by a strong acid, so I'll let you, you can read through that, but here's the chart. So I'm starting here, and it's coming down just the opposite way here. So I'm now titrating it with the strong acid instead of the strong base. Everything's the same. And once again, this would be the buffer region here. Here's the equivalence point. It should be lower than 7, right? Because the conjugate acid of a weak base on its own in water is going to do what?
I was going to bind to
It's going to
make hydrogen.
It's going to have the H come off,
Make
which will
hydrogen.
then bind to the oxygen on the H2O, forming the hydronium ion, creating a slightly more acidic. So the pH should go below 7, right?
Nice.
The weaker the base, versus the stronger the base, the stronger the weak base. How would that adjust where this is? Should do the exact opposite of what you saw from the acid, right? Exactly. This is the exact opposite of the other one. Okay, so here's the equivalence point, it's below the 7 here. The halfway point of the pH is going to be, or the half equivalence point is going to be, so what's this here? What would that amount be? 25 maybe?
25, yeah.
So about 12.5, so this would be about 15, so somewhere right about here. There you go, there's your half equivalence point,
Where the pH.
where the pH equals the pK. That's once again, that's still the pH and the pK there. Okay. pH starts higher, obviously. Equivalence point is less than 7 because of the hydrolysis of the salt. And half equivalence point, pH equals pK. Just the inverse, it's the exact opposite. So of course I'm going to ask some kind of question where you have to identify different parts on here. Right, some kind of a multiple choice or whatever. But it's these, I mean, they're not really, I've already pointed out all the major things that you need to know. Okay, so here we're just doing the exact opposite of what we did, or we're doing the same thing, just we're looking at it from, we're now looking at the KB instead of the KA, and here we're just looking at the pH at the, so here's at the equivalence point, I'm starting with ammonia, a weak base, and then I'm titrating with the strong acid. Okay, and we're gonna do the same thing, so this will give you a chance to go ahead and work on these problems at
The
home.
weak base, yeah.
Right, I don't need to repeat this here, right?
Yeah, no.
So you can solve those, and if you want, what do I have here? Okay, that's, you already know that. And then you do this, and then you do this, you're just doing this whole thing again. And then you get your Ka, and then you do this, and you end up with, what I'll have you do is you could write down the pH here as 5.19, just write that number down, and then try to solve that problem at home. Is it in the notes already solved, or?
No.
Okay. So just solve that one at home. There's one of your problems to solve. It's essentially the same thing we just did, it's just with a weak base instead of a weak acid.
Yeah.
Okay? So my suggestion is just to write that down, solve it, and then if you have problems,
I think
we
it's
can do
in
it
the
here.
back.
Yeah, it's in the back, okay, good, so, okay.
Yeah.
Okay, good. Okay, well, what do I have here? Oops. Acid is expected, okay, good. Okay, now, titrating a polyprotic acid. Looks like this,
Oh,
right? I have two equivalence points, one for each of the hydrogens. If there are two, if there are three, I'd have one for each of those three, so there'd be three. No big deal here. I'm
Gotcha.
starting here, remember the first one actually starts more as a strong, right?
strong, right?
Yeah.
And then the next one is
It's
gonna be a little weaker and,
a little
yeah,
weaker, yeah.
and you'll start a little higher. The first equivalence point, so somewhere over here, you're dealing with, if this is, let's see, this is, so I'm calling this a weak diprotic acid here. So that means that this one would be a buffer region, that would be the buffer region for the second one, even though you usually don't think of it that way. I look at the first equivalence point is at 25. Is the second one also at 25 mils? Why?
It's another path, molecule.
Because once again, you're putting the ratio of the hydroxide to the hydrogen ion, right?
Mhm.
Is the same. This just gets rid of the equivalence point. What did I do? I got rid of all the first hydrogen. It takes me the same amount of hydroxide to get rid of the second one, right? So that's why these are always going to be the same, the amounts. That shouldn't be that. That's just based on, the stoichiometry of the getting rid of one hydrogen with a certain amount of hydroxide. Therefore, I get rid of the second one with the same amount. It might be a little slower process, but it's still the same amount.
Okay.
Right.
Okay.
Right. Okay, so that's all this is. Nothing big. I don't expect much more than that.
I was gonna ask you, so what was the effect of actually getting stronger or weaker? But yeah, it's just the same amount of
Yeah.
slower
Right.
pace.
Well, but if you do look at the chart, though, there are clear differences, right? This is up here.
Right.
This is down there.
Stronger.
And yeah. So where they are would tell
Weaker.
you some information, but just the amounts that you're adding is just going to double.
Okay.
Okay, so now what do I have here? Consider three titrations. What do I have? I have a 25. I have a monoprotic weak acid with a strong base. I have a diprotic weak acid with a strong base, and I have a strong acid with a strong base. What is it? Oh, it's not asking anything? What, you guys?
No, the questions is on the bottom.
Most likely to be true.
I
So
think you
Oh,
gotta go
which
to
one
the
is
next
most likely, okay.
You gotta
So-
go to the next one, next slide.
There's
I don't have
another
anything on the
slide.
next slide.
Oh.
So, okay, so what do you guys think? Which one's most likely to be true?
Oh.
Look, these are the options. The pH, this
Oh.
or that.
Which, oh, I see.
Uh-huh.
All three titrations have the same initial pH?
No.
No,
No, why?
they monoproduct, diproduct, strong acid, yeah. It's going
Okay.
up this there.
All three titrations have the same pH at their first equivalence point?
No.
No, why?
They still also starting at a different level.
It's different than pH.
So, the same pH, right, because the same pH at the equivalence point, this one would be 7, these would be above 7.
Yeah.
Okay, good. That's, I mean, that's all you're evaluating here, right? Okay. All three titrations require the same volume of sodium hydroxide to reach their first equivalence point.
No, yeah,
Yeah,
that,
yeah, absolutely.
This is
The
all
same volume
25.
within themselves.
Because you're just looking at the OH pulling off an H.
Uh-huh,
And they specifically stated their first equivalence point.
right.
So that means the reason for that is because the diprotic has 2 equivalence points. So it's saying the first one.
Mm-hmm.
If I said the second, if I didn't say that, if I go to the second one, it would have taken me double.
Right.
Okay, so then what that says is C would be the right answer. Everybody see that?
Right.
Any questions on that? No? Okay. And good, that gave me a chance for you guys to see how I think about it and how I would evaluate. That's essentially like a test question, right? And that's how I evaluate those questions. Okay. So, okay, here we're now getting into the indicator part of the titration. And the change in, so the only thing I'll point out here is that when you think about using an indicator and you see the color change, that's called the endpoint. Ideally, the endpoint is the equivalence point, right? But not always, because you can't always get the indicator right there. In fact, phenolphthalein, that isn't right at the equivalence point when we use the strong acid, strong base titration, just so you know. And we'll take I think we might get a chance to see that. So the endpoint should occur at the equivalence point. At the very least, it should occur close to the equivalence point. Otherwise, it's not really that useful as an indicator for what you're trying to solve. But if it's not at the equivalence point, then you simply call it the endpoint, and that's just the color change of an indicator. That's it. Okay. I'll show you here. Okay, here's phenolphthalein. So it has when it's in an acidic environment, it's colorless. So if you remember, you had a Erlenmeyer flask with acid in it, and you put a couple, remember, one other thing I want to point out. In the indicator, you're only putting in a couple drops. It's a very small amount relative to the total volume you're using, presumably. So keep that in mind. And you put it in the Erlenmeyer flask, you have some acid, and you put the phenolphthalein in there, and it's clear. You titrate through the base, which I think we use sodium hydroxide probably, and when you got to the equivalence point, or I should say the end point, as now you know, since they're different, most of the time, then you saw a pink color. When it was lightly pink, that's as close to the end point as you can get. The stronger pink it got, the more you now have crossed over on that curve further up here, right? So the curve goes like this, you're way up here. And the indicator is telling you where you are on that curve, essentially, at least at some point where the color change occurs. Does that make sense? Okay. So when this is the phenolphthalein molecule. When it's in the acid, it has this conformation. When it's in the base and it looks pink, it has this conformation. So what happened?
You break up the H?
This H left, this rearranged here, this is left there, and then that caused this to open up and rearrange. All the kinds of things you're going to learn in the next semester, how those things occur.
Can you replace back?
Yes. If I now put this into an acid, the hydrogens now could bind here, rearrange, this could bind to hydrogen, and these would rearrange back. And if you didn't know that, how would you know that? You took 101 with me.
Yeah.
Did you or did anybody in the lab go so far over and I said, why don't you add a couple drops of the acid back? Did it turn from pink back to clear?
Yeah, I did that.
Yes, there you go. And that's your evidence that yes, you can go back and forth,
Nice.
right?
Awesome.
Cool. Okay, so this is just the phenolphthalein with, its full conformation, and then this is when it's in a different environment. The other thing, I gotta make sure this is in the proper perspective. This is in the environment of an acidic solution. This is in the environment of a basic solution. So what I'm saying there is that I have something like this, and I have that in there. And when this is favoring, let's say in an equilibrium, is favoring the basic side, then it's gonna favor this conformation. And that's what I'm gonna see visually. And that's what an indicator does. Okay, let's see how we follow along with that idea. Okay, because this is the tricky part of it. So if I look here, here's an indicator in its acid form. I put it in water, I get an equilibrium, I get the hydronium ion, and I now get this here, the conjugate base of the indicator. Okay? So this is outside of a solution. Okay. So now in a solution where I have, let's say, a weak acid and a strong base, or just a weak acid, if I have a weak acid, I'm gonna have, this side is gonna increase, and what's that gonna, how's that gonna shift the equilibrium of the indicator itself? It's gonna shift it this way. So in an acid, it's gonna look more like this, hence more like that. That's really important, what I'm saying there. It's hard to reconcile that sometimes. You just wanna look at this linearly. If you just look at it like this, that is the equation for the indicator with water on its own. But you don't care about an indicator on its own in water. You care about the indicator in the context of some solution or something. And that's where it has a role. So when I look at this equation, I'm not really I'm seeing this, but I'm saying if this is in an acidic solution, then it's gonna shift this way, and this is what the indicator is gonna look like in that solution. If I have a basic solution, then it's gonna pull some of this out, and it's gonna shift it this way, and this is what I'm gonna have in the solution as the indicator. And that's a tricky thing to think about, because you're holding two things in your head at one there. Usually you're just looking at that one level thing. That's kind of the complication here, right? You do this first, and then you have to recognize I have this, and I have to now do a whole new equation to see where I'm at. You're doing more than one thing in each case.
So even though the indicator is such a small amount, it actually can have a little bit of a reaction there?
It is reacting, that's exactly what it's doing. But it's doing it based on the conditions of the solution, and that's the key, yes. If the solutions are acidic, then you're forcing it this way and you have this. If the solutions are basic, you're forcing it this way because you're pulling that out, and now you have that. And that, whether I have this or this, will indicate the color of the indicator at that point.
I see.
But it's not gonna do anything to our
But
solution
you-
itself.
It shouldn't do anything to your reaction itself.
Is that why you
Shouldn't.
only put like a couple drops in?
Yes, because you sure don't want it to,
Oh, okay.
you don't want it to have an effect, and maybe it doesn't depending on what reaction you're doing, or maybe it does.
Gotcha.
It's
Give it
still,
too
on
much
its own, is
age.
forming this,
Okay.
right? So if I put this on its own in water, or I put a base in, I get the reverse. Then I don't want to create too much of this as a result of that, because that's gonna
You're
now
not being
be
trained.
factor into what I'm doing with my
Acidic
acid
reaction.
base, absolutely, yes,
Okay.
yes, yes, yes. Okay.
2 far drives.
Okay, so, okay. I'm gonna walk you through real quick here just to give you a sense of this, but it's not likely, I'm not gonna really bother a lot of this. This is, we don't have any real examples to show you here. So, just so you can see, you can get the pH of the indicator by using the pKa of the indicator, and then its ratio of its base to its acid, okay? I'm not gonna really ask you to take the pH of the indicator though, but you can get it. That's all I'm pointing out here. No big. And once again, you see I do indicate this means the pK of the indicator, not of the solution or whatever acid that I'm looking at, right?
Okay.
Okay. Additionally, just like any of the other things for the acids, you can do the pH relative to the pKa, and you want to go +1 and -1, and that should be your range of your
The pKa.
indicator. you know, here you have your intermediate color, over here you're gonna have your color of this, and over here you have your color of that. Whatever it may be. It could be a lot of different indicators. This is just a standard for any. Once again, this is the same thing we looked at with just acids on their own, right? Now I'm just looking at the indicator, but once again, I'm not gonna ask you to do that for the indicator itself, per se. Because the indicator, it's gonna matter in its solution, not by itself. But you can figure out what they are by themselves. And here's just the pH range of a couple different indicators. I don't even know why we have this on here, because I'm gonna show you a bigger chart. Okay. That's the chart here. Okay. What this shows you is, here's the pH going from 0 to 12, and these are the different indicators here by name, and these are the regions where, when the pH is at that point, they'll have some kind of a color change. So over here, I'll see yellow down here, blue over here. I'll see red here. When I get a little over 2 pH, I'll see yellow. That means anywhere from here to here is all yellow. Anything from here to here is blue. Okay? But this one has 2 spots, so when I get over here, the thymal blue, when I get just above 8, I'll see the yellow change to 9. Okay? So what does that mean? If I have a solution and I want to do a titration, and I titrate, let's say a weak acid up through with a strong base,
So good as
and the
well.
equivalence point I know in that solution is somewhere over here,
Okay.
then this would be a good indicator to use to see where I hit that equivalence point. That's what this means.
I'm a blue.
Okay? That may not be what the pH of the indicator itself is, though. You see that? I'm not looking for that. I'm looking for where I get a color change for the pH at the equivalence point of an acid-base titration. Okay? And by the way, here's phenolphthalein over here. You can see it changes from clear to pink right around, what is that? 9. In the basic region. That's a little outside where you actually had, I think you might have been 65. Did you do a strong acid, strong base titration?
Yeah.
With phenolphthalein?
Yeah.
So it should have been 7, right? That's a bad indicator for that. But it's also very cheap and easy to use.
The better one to use beef.
Right?
Oh, wow.
But now you're getting a sense of this, right? And I think, and later on, I think we use, what do
Thymal
you use?
blue. We
Is
did
it
use
thymal
thymal
blue
blue.
or some kind of blue or
We use
something?
thymal blue.
Yeah.
Thymal blue, so that's because it's over here, that's a lot better.
We use bromocresol as well.
That comes here, this goes
What
over
about
here.
Fetal red.
Phenol red comes over here, so that would be a good one, if it was available and cheap.
Yeah, but it's.
Right? So now you see the remember all those things I was telling you last time, that you gotta take what you have and do the best you can with it. And then you gotta understand the different things associated with it. So here you're getting a sense of that. So let's go ahead and take a look. I have a sample of rainwater that gives a yellow color with methyl red. Okay, so here's my methyl red, and it gives a yellow color. So approximately, what is the pH of the rainwater? 6. Okay. And I'm sure that's what it's gonna tell me, 6. That's really not the way I would have thought. That's a horrible, because it's really any 6 or above.
Yeah. Yeah.
That would be the more appropriate way to say it. Okay, just to keep that in mind. Okay, so what's next here? If bromothiamyl blue was used, and now I'm saying this is the bromothiamyl blue, you would have a chart here, by the way. I wouldn't just expect you to
Okay.
know this.
Bromothiamyl blue.
What color would be observed with the
Forward.
with the rainwater?
Oh, blue.
Oh, yellow.
Blue.
Whoa.
Because we know that the pH is 6, so it would be blue. Right? That make sense? This one should be really, really easy.
Yellow.
This,
On that chart that they show.
Oh, not the original chart.
It's,
The original chart is
the
different.
original chart.
I'm
said it's gonna be
looking at this
yellow.
one. We're just looking at
Okay.
this one here,
Okay, okay.
right? That's why I put it, that's why I put this up.
Yeah.
This is up here, this is what we're using. I'm just asking about rainwater.
Okay.
And I'm saying, what is the approximate pH of rainwater? If rainwater gives a yellow color with methyl red, I highlighted that this is methyl red. It gave a yellow color, so we're saying the pH is really 6 or above, and that's good enough. Then I'm saying if I use bromothiamyl blue with that same rainwater, what color would it be? And it would be anything above blue because it's 6 and above, so we know it's above It's gotta be blue. That's all I'm saying there. That should be pretty simple. There's nothing more than that there.
And just that this one didn't have the little chart.
What's that?
This one didn't have the little chart, so it couldn't.
Right, no, that's okay, but that's up here.
Yeah, okay.
Is that okay? This could be like a test question, right? You have to be able to figure it out. Not too difficult. Okay. Propionic acid is a weak organic acid. It has this Ka.
Oh,
Which of the indicators listed below is the best choice for the titration of propionic acid, weak acid with a strong base?
so you get
This is a
the-
completely different question than the last one, and I have to point that out, because that's where most of you will get stuck if you're not sure. The first one I said, here is rainwater. Rainwater gives you this pH essentially. Here I'm not telling you that. What am I telling you?
You get the Ka.
Giving us the K, can get the
I'm
PK.
telling you the titration. There was no titration in the last example. It was just rainwater. You figured out the pH of it, and therefore if I used a particular indicator, what the color is. Here, this is a titration. This is not just rainwater. I didn't take rainwater and titrate it with sodium hydroxide and say it was acidic. Keep that in mind. I just said rainwater. Here I'm saying you have propionic acid, and I'm titrating it with potassium hydroxide.
Strong base.
What indicator do I use? You see the difference between how I'm asking? That's really, really important.
Yeah,
So here, I have methyl red, which is right here. I have bromothiamyl blue, which is right here. I have thymyl blue, which is right there and there. And I have alizarin yellow, which is right here. What do I need to do to figure this problem out? That's what my question is here.
find out what your pH first is.
Where should my pH be approximately? At the equivalence point. Huge, much different than that last question. What am I using the Ka there for? Am I getting the pKa and all that? No. Then I'd be looking for what? What color would be if I had propionic acid by itself? But it's not, it's being titrated. So in that titration, the Ka can kind of help me because it can kind of tell me maybe how high or low the equivalence point is relative to a weaker or stronger acid.
Okay.
So here, this is a weak acid, strong base. Where approximately, relative to 7, where am I going to be, above or below 7?
Above.
Above. Is this a relatively strong weak acid? That means it starts a little lower, and therefore its equivalence point is a little lower relative to a weaker weak
Right.
acid.
Okay.
So this maybe would be somewhere, let's estimate, 7.5 to 8.5. Estimate's better to estimate, you think of a range,
Right.
right? You don't want to estimate it. If I say between 7.5 and 8.5, do I have a much better chance than saying 7.45, 8 point? Yeah, absolutely. It's in a range. That's all you're doing there. You're not asking, you're not looking anymore. So then I come over here. I'm looking somewhere over here, right?
It says thymal blue.
So I see there's thymyl blue,
Yeah.
But then there's also bromothiamyl blue, which covers more range.
but we're bromothiamyl blue. So where is that one?
But that's all over between three.
No,
That's-
In between it's,
That's barely.
Where would it
touching.
actually change?
it was
Fine.
7
Yeah, it's
oh,
barely.
okay.
Yeah.
Ah,
Mhm.
right? So then what would be the best, and this is way over
Thymyl
here, it's,
blue.
right, it's changing there. So this would probably be the best one, thymyl blue.
Yeah.
Hopefully we're right. But you see though, the instinct isn't that. The instinct is to start trying to figure out what the pK is and then try to figure it out relative to the propionic acid, because that's exactly what we just did with the rainwater. Because that wasn't that wasn't a titration. Hence the difference on how I made that determination.
Mhm.
I was utilizing the information I understand about indicators, but I clearly wasn't doing any titration with it. It was just a standalone rainwater.
If you do put a strong acid and a strong base, then you go with anything that is in 7.
That's where you estimate where it's at, yeah. So you could actually figure it out because you already, if you had the proper information, you could figure out the pH exactly.
Mm-hmm.
But I would need to give you volumes and concentrations, and then you would do all the things we did to get here.
Right.
Right. Good. Okay, so now, HF has this 3.5 times 10 to the minus 4 Ka. So it's a weak base, but a weak acid, but it's a fairly strong weak acid, right?
Yeah.
Yeah.
So once again, what range am I looking at? Probably somewhere around here.
Same again, yeah.
So let's go through now. Remember, there I gave you specific choices. Now you have all the choices. So now we could probably pick something maybe better than Thymo Blue. That was just better than anything.
Phenol red.
So maybe, okay, that sounds pretty good, going from yellow to orange right around here,
Nitrophenol? Why
right?
not in
Maybe even M nitrophenol, even though I can't really
That's
see the
just
color
all
change
red.
personally,
Oh.
but I guess let's assume there is a color change that I can't see with my eyes. Then that would also be okay, because they put it there, so there must be some change that I'm not recognizing. So
Yeah.
yeah, right in there looks bright, that looks, yeah, there we go. That's exactly right.
phenol red or
Whoops. What about this one?
HCN? So that's a very weak acid.
So the first thing is, the Ka from this one tells me something significantly different than this.
Yeah,
What does it tell me?
it is a lot higher.
It's gonna start a lot higher, and therefore the equivalence point will be a lot higher.
Right.
Remember that chart I pointed out where I showed you those, the weaker and stronger acids? So I'll take you back to that in a second, but, so with this one, we know that the pH at the equivalence point is gonna be much higher, somewhere over here.
Phenolphthalein?
So maybe,
Phenolphthalein is cheap.
maybe alizarin yellow, or maybe this one a little higher.
Oh, that
Maybe
much
this
higher?
one could, thymo, somewhere in here maybe?
Why would it be so basic for its
I'll
equivalent?
show you in a second.
Because it's very weak.
I'll show you in a second. It's a good question. This is, okay, alizarin, okay, so are we okay here?
Yeah.
Okay, now, just to get to Jenna's question, let's go to here. Here, right?
Yeah, yeah.
Look at the different KAs. So that one was up here. So look where this one is starting versus where the other one was starting. And now its equivalence point is gonna be way, way up here. Why, now that just gives you a sense using this chart. The other part to your question may have something to do with as well as, why is that? And that's because it's a
Weak acid.
weaker acid, which means it has a greater affinity.
Uh-huh.
It won't dissociate.
It won't dissociate as
That's
much.
nice.
So then you take its conjugate base
And it's gonna create
with
more of it.
water,
Yeah,
it's gonna pull them even more so off, creating more hydroxide.
right.
Does that make sense, Jenna?
Yeah.
Okay, good. Okay, right.
Yeah.
So this just kind of gives you that visual view, but that's the intellectual component of it.
I like it.
Okay, so that covers titrations for us. Now I do want to get going right into,
Chapter 18, I'm just kidding.
we're still in 17, that's the problem. But I want to jump as quickly as possible. I'm not going to take you too deep. This is a complete, this changes a lot and this gets really tricky, and I think that this is more challenging than the last one, but I want to get you going in it so that we can finish this one on Tuesday. So this is the third part of chapter 17, solubility equilibria. Okay? I'm going to show you things called KSP, solubility product, and then how the common ion effect plays a role. We're going to look at precipitation calculations. We're going to do some things called fractional precipitation, complex ion equilibrium. I think I mentioned this with aluminum 6H2Os a while back, right? And then we'll get, this is called the K of formation of things. We'll get it, I'll briefly cover this. Amphoteric hydroxides, I'll probably cut some of that out because it's not as relevant and we don't have as much time, but I'll touch on it just so you have an idea about it, and then complex ions and solubility. Okay, so let's do this. What I want to introduce here is this, the term what was solubility? Remember that term from 101?
It like
Yeah.
solves.
Solubility comes, is the precipitation or not? Precipitation?
Solubility is the amount of something that you can dissolve
Mhm.
in something, right? Before it comes out. So we saw solubility charts where we had these little things that went up like this, the different salt things. And when you were above the line, you were saturated. When you were below the line, you were unsaturated. And what was the gauge there? That was in the volume of water. It was always odd, given by like 100 grams. And like why mass? But of course, 1 gram per mil was, you can convert that to milliliters. That was on the y-axis, right? And then what was on the x-axis? What was the other component there? Temperature, remember? It's temperature, okay. And then you saw these curves, right? Remember the sodium chloride curve, for example, solubility of sodium chloride in water, solubility? It was just a straight line around 30. So that was what, 30? 30 what?
Hmm.
No, the degree Celsius was just going across like this. But what was this supposed to be representation of? 30 grams per 100 mils of water. And it had that, if I put more than 30 grams in 100 mils of water, it was now saturated. If I put less, that's how much I could dissolve at those particular temperatures.
101?
You guys don't remember that? Yeah,
Yeah, I
that's
remember
101.
Yeah?
Okay, that's, what am I doing? I'm just telling you, reminding you what solubility is,
Right.
okay? So, we had solubility rules too,
Yeah, I remember this.
right?
Yeah, the rules, yeah.
Is something precipitate or not,
Uh-huh.
okay? And we just looked at the insolubility rules. Okay, so that's solubility. Now, if I take something that's a solid and I put it into water, I see that sometimes it doesn't all become either soluble or insoluble, right? Because the solubility rules and the solubility chart, two different things that both deal with solubility. One dealt with the saturation of something in a certain volume at a particular temperature, and the other one dealt with whether or not it formed a solid or a precipitate in water or not. And it either did or it didn't, right? There wasn't any medium ground. But do you think that some of those precipitations were just 100% precipitate?
No.
No, no. I have this CaF2 in water, and it's a solid. Some of it actually goes into its ions in terms of the form. They call that dissolution, and then some of it comes back into an equilibrium, which now you're really, really familiar with. I'm probably getting tired of it at this point. And I can get an equilibrium of this. This is called slightly soluble solids. All right? This is starting to, so you see where we're going with this?
Yeah.
Okay, good. But you also can see, look at the ratios are different. They're going to be different and start to change. Keep that in mind, the stoichiometric ratios there. Okay. So then from this, we could create, our constant is going to be called the solubility product constant. Okay. And that would be what? So in this case, what would be my solubility product constant? That would be KSP equals what?
Say A times the 2, well, to the second power.
Yep.
F to the second power.
That 2 comes here. Just like you guys learned, except for you learned it a long time ago.
We just learned it. We did it in the lab right now.
Oh, you did? Oh, good.
Yeah,
Okay.
So there we
Oh,
go.
That's the only
perfect.
reason we know.
Okay, good. Because this is what we did, remember, in lecture quite a while back.
Yeah.
Right, okay. Okay, so that's all this is. So this is the KSP. This is dealing with slightly soluble solids or precipitates. Okay? So you always have some level of residual going back this way, and therefore you can calculate those things. Okay, and that's called the KSP. Okay. So now, okay. So the KSP, so here's a chart here with different precipitates and their KSBs. So what does that mean? What is a higher KSB versus a lower KSB?
Oh, more solubility, more precipitate
Higher KSB means that
Higher.
more of them go into the
into the
ion form,
Yeah.
right? Lower KSB would mean that less of it goes into the ion form, more of it stays in its precipitate. The simple description of one of these constants, one of these Ks, right? Equilibrium
Oh,
constants.
we did Q's differently though. It's
Q's
like-
different.
Oh, okay.
Q means you're not at equilibrium. You're
Gotcha.
either before or after equilibrium, but it helps you figure out where to go for equilibrium if you know equilibrium.
Okay,
It knows what direction you'll be moving,
gotcha.
right? Okay. Okay, so these are the different KSBs of these different things. This is just called a selected because, certain things that are more common, solubility product constants for different compounds. Okay, go ahead. Carl.
Those would all be at one temperature.
Yes. We're gonna assume that we're sticking to a,
25?
to a particular temperature.
Because in the lab, like, that was one of the things mentioned.
That was it.
Is,
Important.
if your experimental range for your KSP is different from the literature value, one of the reasons could be.
Absolutely,
temperature.
and you can see that, right? Well, going to the solubility chart that I brought up earlier, which is exactly what that relates to, the temperature. and I brought up sodium chloride. Did sodium chloride change in its amount that would be soluble or insoluble? With the temperature? No. And that was
No.
weird, right? It was exactly 30 grams all the way across. Most of them do what? Can I usually dissolve more or less with a higher temperature? More. Right? So for example, if I put sugar in coffee or tea or whatever.
Yeah.
If I heat it up, I could put more sugar in that if I really like it, right? I could dissolve more in it. Same concept. But what if I have something that's over 100 degrees?
You're just gonna say sink to the bottom.
Don't drink it? No.
Well, it might chemically change.
It would appear what in an experiment?
Oh wait, 100 degrees over that.
And of course, my solvent is water. Let me make that clear.
Mhm.
Say that. Well, you're going to have some evaporate, which means that you're going to reduce your volume of water. So it's going to look like you can dissolve less, right? But that's more of a mirage, because in reality, if you heat it up and you kept it all together in one area, you should be able to dissolve more,
Okay.
right? Does everything always dissolve more with? What was something that didn't? There was one thing on that chart that actually started over here and it went down, as opposed to up, as I increased the temperature. I think in my class, I pointed that out, and I probably gave you some back, and this may go back to 65, by the way. This might be a 65 topic, not a 101 topic. So in my 65s, I always explain what that means, right? It's the way that the molecules are interacting with each other at a particular temperature. And there was one on that chart that actually went down with the increase in temperature. That's the only one. And most never got all the way over to that 100, because at 100, once again, you can't accurately identify how much you can dissolve, because now you're
Lots of
reducing your
water.
overall volume of water.
Mhm.
So it's not 100 grams anymore, which
Right.
is what that table was based on. Okay. So yes, that can change for your, and you can see how there.
What was that molecule? That didn't change? That
Oh,
actually
I don't remember the name of it, but it's an ionic compound
Uh-huh.
that actually you can dissolve more in
in colder temperature.
if, or I should say, you dissolve less in at a higher temperature
Higher,
than
right.
lower temperature. Yes.
Okay.
Okay, so now we're gonna real quickly go through KSB and the relative solubility. So the molar solubility is exactly what I just described, right? It's dissolving a certain amount of something in a certain volume. But the KSB is just how much it breaks apart. But what would the correlation be there? What would you expect the correlation to be? Higher KSB means what?
That means
More
more breaking up.
Less.
More ions.
More ions, yeah. Breaking up.
Ions in water do what?
Breaking up dissociate?
Dissolve,
Right.
right? The precipitate means it comes out of solution, sort of the whole thing I was talking about with solubility, that solubility
So
chart.
if it's really soluble, have a
So the higher the KSB, you would expect
more solubility.
more solubility.
Mhm.
Higher, okay. Now that's what doesn't always correlate. Okay.
As we found.
Right. Oh, did you? So okay, so this is, okay, good. So now you'll maybe see, go ahead.
So if you have a smaller KSP, you'll have more precipitate,
No.
or is it the opposite?
Yeah, more precipitate, yes. More smaller,
You're right, with lower.
Yeah, the higher KSP.
What?
So
The
smaller
lower
KSP
KSP,
is
less-
more precipitate.
and less-
Larger
Watch.
KSP is a smaller precipitate.
Just do it like this. Let's say, what was that? What was the one I had up there? Let's say HF. Maybe it was not HF. And it goes this way, and you get H plus F minus. This is a solid, okay, let's say. So then the KSB is what?
8.3
This times this.
Yeah.
squared.
The higher,
Oh, no,
Jenna,
single, no.
the higher the KSB means what?
It'll-
More of this.
Yeah,
Which means you have more ions.
which means you have less of that.
Yeah, right.
Okay,
Is that okay?
that makes sense. No, yeah.
Hmm?
Yeah.
Oh yeah, less precipitate, yeah.
Less precipitate.
Uh-huh.
Yeah.
uh-huh.
Mhm.
Okay.
Okay, so I just talked about the relationship between molar solubility and KSB are not always directly related in two different compounds. Okay, so let's take a quick look. Whoops. So I have magnesium hydroxide and FeCO3. What was that? Whoops. Here's the KSB for the magnesium hydroxide. And the FeCO3 is what? Iron carbonate, iron 3, 2 carbonate, huh?
And it's higher.
It's higher. But what about the solubility?
Lower.
It's
lower.
inverted.
It's the opposite.
It's the opposite. For this, though, that's intuitively not right.
Yeah.
You would expect these to follow along. Why is it different?
Because they're different.
Molecules?
Because of the range.
How many of these am I going to get here?
Two hydroxides.
2. So I'm going to see what? I'm going to see more solubility
Higher power.
because I have more molecules, more ions there coming out each
Power.
one.
So in lab, the first part of the lab, we were looking for the solubility of calcium iodate in water.
Okay.
And
So
the
that's
second one-
CaI2.
Yeah, CaIO3 too. And then the second one, we did calcium iodate and potassium iodate to try and achieve the common ion effect.
Okay.
And I think we found that the KSP was larger, but the solubility was high.
Was lower?
Smaller, yeah, so it was the opposite in lab. That's
Yeah,
why it was,
it's kind of like this.
It's kind of, yeah.
Oh, yeah, like this.
Yeah.
Okay. I'd have to see which, we'll put up those
Okay.
molecules. If you want to bring them in, we can put them up and then we can see why. But I'm gonna discuss, I guess I'm out of time, but I'm gonna
So it's the
discuss.
same thing.
Oh,
I'll discuss, I at least wanted to get into this.
It's actually
and
that
now
same thing.
I think
It's the same
because
thing.
Calcium, you have two.
The same
and
concept.
potassium, you have
Yeah,
one.
it's.
Yeah,
Calcium,
and
you
that's
have
why,
it too.
because of the
Yeah.
ratio, and I'm gonna tell you more about this. We'll pick this up on Tuesday next week,
That's your report.
okay?